Welcome to the Deep Dive, the show where we take a stack of groundbreaking research and, well, basically turn it into a shortcut for your brain.
That's the goal.
Today, we're plunging into one of the most persistent, beautiful, and just utterly perplexing mysteries in all of physics.
Oh, I know where you're going with this.
The fine structure constant, alpha, right?
See.
This isn't just any number. It's a dimensionless constant sitting stubbornly at approximately 1137.
Approximately, yes. It's measured with incredible precision now.
And it fundamentally dictates the strength of electromagnetic interaction. I mean, for decades, brilliant minds have wrestled with why this number, why precisely this value.
It's like the universe has this secret dial, doesn't it?
Yeah.
Set perfectly to 1 over 137 point something.
Exactly. And we've never known who said it or, more importantly, why.
Indeed. It's fundamental. It pops up everywhere. Governing energy levels in atoms, dictating the very fabric of chemistry, how light interacts with matter. It's crucial.
Crucial for the stability of matter as we know it. Yet its origin, it's remained elusive. A really profound, almost philosophical puzzle for physics.
Absolutely. Richard Feynman, the Nobel laureate, he famously said something like, all good theoretical physicists put this number up on their wall and worry about it.
That perfectly captures it, doesn't it? The enduring frustration and, well, the fascination surrounding alpha. And that's why today's deep dive is so potentially revolutionary. We're exploring a radical new framework. It's proposed by Philip Randolph Lillian in his work, 22nd Century Coherence Physics.
And it really is radical. This isn't just a minor tweak or a slight adjustment to the standard model we're used to.
No, it's a profound reinterpretation of how the universe's fundamental forces actually operate. The big idea here, the truly paradigm-shifting concept, is that fundamental interactions, the very fabric of reality, they don't arise from arbitrary coupling constants.
Those dials we just talked about.
Right, or from traditional separate forces that we then try to patch together. Instead, they come from what Lillian calls coherence reduction pathways.
Pathways within a singular underlying field. That's the key.
So what's truly groundbreaking here is this conceptual leap, right?
Right. Instead of forces being the primary things, the entities that we then try to unify later on, coherence physics says they all emerge.
Emerge from something more fundamental.
Exactly. From the way coherence is lost, or perhaps more accurately, how it's redistributed within this universal field tensor, or UFT.
UFT. And Lillian describes this UFT not just as a mathematical tool like we sometimes use in physics.
Not at all. He posits it as a fundamental physical substrate, the bedrock from which everything we perceive actually emerges.
Okay. So our mission for this deep dive is to unpack this incredibly complex, yet it sounds like elegant idea.
It has a certain elegance, yes.
We're going to try and move beyond the jargon as much as possible to really reveal how this coherence physics doesn't just explain constants like alpha.
Which would be huge in itself.
Huge, but it actually derives them. From first principles, we'll see how it radically redefines nuclear stability, how nuclei hold together or fall apart.
And even how it subtly influences chemistry. That's a really surprising connection.
Isn't it? Get ready for some serious aha moments, because you'll discover how everything from, say, the immense power of nuclear fusion
To the mysterious nature of black holes.
might just be governed by this single, elegant principle of coherence. We promise we'll give you that shortcut to understanding this potential paradigm shift, complete with surprising facts, enough detail to make you feel well-informed, but hopefully not overwhelmed.
We'll try our best on that last part.
You'll walk away with a completely new perspective on the fundamental nature of reality, hopefully. Okay, this all sounds incredibly profound, but, to truly grasp why it's revolutionary, we need to understand the problems coherence physics is trying to solve. What are the current frustrations, the unanswered questions, and how we describe the universe's forces right now? Why do we even need this new framework?
That's the essential starting point, isn't it? And it raises that important question. If these fundamental constants aren't derived from our current theories, are we just missing a deeper underlying principle?
Right. Are we just scratching the surface?
Exactly. The problem with our current force-based models, especially quantum field theory, really boils down to what physicists often call arbitrary constants. We have these numbers, these coupling constants.
Like the strength of electromagnetism or the strong nuclear force.
Precisely. We measure them in experiments with incredible precision, fantastic precision actually, but we simply don't know why they have those specific values.
They're just inputs, parameters we plug into the equations.
They're inputs. They aren't derived from the theory itself. It's like, the universe came with this incredibly precise set of dials, and we've only ever been able to read the numbers displayed on them. We've never understood the mechanism that actually set them.
So we've got these numbers, like alpha being roughly 1137, that we found through meticulous observation, decades of experiments. But our best theories basically just say, well, this is just what it is. It just is.
Pretty much.
That sounds like a really foundational gap in our understanding, almost like a missing origin story for these fundamental parameters.
Precisely. And this issue kind of extends to other areas of modern physics, too. Think about renormalization schemes.
Oh, yes, the mathematical techniques to deal with infinities.
Right. These are highly sophisticated, very complex mathematical procedures physicists use to handle infinities that just keep popping up in calculations within quantum field theory. Now, renormalization has been incredibly successful. It lets us make remarkably accurate predictions that match experimental results beautifully.
So it works.
It works, pragmatically speaking, but some prominent physicists view it not as a fundamental solution, more as a workaround, a very clever, essential workaround, but maybe not the final word.
Like sweeping the infinities under the rug, making the calculations work, but not fully understanding why they arise in the first place.
That's one way to put it, perhaps a bit harshly. It's more like we found a systematic way to subtract the infinities that yields the right finite answers. But the reason those infinities appear and why the subtraction works might point to something deeper we're missing about the theory's structure at very small scales.
Okay. And then there's the idea of fundamental gauge groups, these mathematical symmetries.
Yes. Our current theories, especially the standard model of particle physics, they assume that these mathematical symmetries, what we call gauge groups, like SU3 for the strong force, U1 for electromagnetism, SU2 for the weak force, are fundamental structures, baked into the architecture of reality from the start.
Like unchangeable pillars of the universe.
Exactly. Think of these gauge groups as the mathematical blueprints dictating how forces behave. SU3, for example, that's what gives the strong force its unique personality-binding quarks tightly, acting over incredibly short distances. U1 defines electromagnetism's long-range pull, its free charge carriers like electrons. Our current models just assume these blueprints exist.
But coherence physics challenges this.
It challenges the fundamentality of them. It suggests these gauge groups aren't the absolute starting points. Instead, they are emergent phenomena. They arise from something deeper.
From coherence.
From the underlying coherence of the universe itself, yes.
Wow, so a universe where the dials and noms aren't arbitrary, where their values are actually derived, that sounds, well, truly revolutionary.
It is. And what's fascinating here is the shift in perspective. From what we might call a force-first ontology, where forces are primary.
Oh, coherence-first ontology.
Exactly. Coherence physics offers this unifying principle. It posits that all fundamental interactions, strong, weak, electromagnetic, even gravity, aren't distinct things that need to be artificially brought together later. They're just different expressions of
coherence gradients and symmetry reduction.
That's the terminology, yes. Coherence gradients and symmetry reductions. This is a really significant departure from conventional unification ideas, the ones that rely on pure group embedding, trying to fit everything into one big mathematical box like SU5 or SO10.
So instead of unifying forces that seem independent and somehow broke apart early on, CP says they all come from this one single underlying principle, like different facets of the same gem.
That's a good analogy. And it introduces this universal field tensor, the UFT, as the actual underlying physical substrate from which everything emerges.
Not just math, but a real physical thing.
That's the claim, a fundamental entity, the ground state of reality.
Okay. And critically, you're saying a major strength of coherence physics is that it doesn't just describe these interactions.
No, it aims to derive the relative strengths of these forces from first principles without needing those arbitrary parameters we plug in.
So those dials we talked about, coherence physics tries to explain how they got set, not just read their current positions.
Precisely. It offers an origin story for the constants themselves, a mechanism, not just a measurement.
Okay, so if we strip away the traditional idea of distinct forces, what does this really mean for how we fundamentally perceive the universe? Is it all about how coherent things are?
If we connect this to the bigger picture, yes, it fundamentally changes our understanding of interaction itself. In coherence physics, coherence isn't just, things being in sync like waves. It's deeper. It's a measure of the underlying order, the structure, the unity within the universe's fundamental fabric.
Okay.
Imagine the universe at its most basic level, like a perfectly structured, seamless tapestry. or maybe a perfectly still, undisturbed cosmic ocean. That's the maximally coherent state.
Pure unity. No distinct forces or particles.
Just pure, undifferentiated potential.
Exactly. Interactions, then, aren't primarily governed by forces in the way we usually think of them. They're governed by how this perfect coherence is maintained, or, more often, how it's lost or maybe redistributed.
Through coherence relationships.
Yes. The forces we actually observe, the ones holding atoms together or governing radioactive decay, they're essentially the universe's dynamic response to disruptions in its perfect order.
Okay, so it's like that perfectly smooth pond, completely coherent. Then our observable forces, electromagnetism. The strong force, they appear when this primordial coherence gets reduced through these symmetry-breaking transitions.
It's the idea, like ripples appearing on that smooth pond. But these ripples aren't arbitrary. Their very form, their strength, it's dictated by the underlying coherence.
And the strength of a force, what we call a coupling constant.
Yeah.
That's directly determined by how much coherence is lost during that reduction. Exactly, the degree of coherence loss. This provides a common origin, a single source, for the strong electromagnetic, weak, and potentially gravitational interactions. Their relative strengths, which, vary enormously.
Hugely. Gravity is incredibly weak compared to the others.
Right. Those relative strengths become fundamentally coherence ratios. So the age-old question, why is gravity so much weaker than electromagnetism, gets rephrased.
How?
It becomes, why is the coherence loss associated with gravity so much greater, or perhaps occurring at a vastly different scale than the coherence loss associated with electromagnetism? It turns a question about seemingly arbitrary strength into one about fundamental coherence dynamics.
That's a really powerful reframing,
Right.
and brings us to how this integrates with our existing standard model, specifically QCD quantum chromodynamics for the strong force and QED quantum electrodynamics for electromagnetism. How does CP see the relationship between their symmetries, SU3 and U1?
Well, in conventional physics, QCD, with its SU3 gauge symmetry describing the strong force, and QED, with its U1 symmetry for electromagnetism, they're largely treated as distinct interaction types, right? Each has its own coupling strengths we measure.
Yeah, they seem very different.
Coherence physics, however, integrates them rather beautifully. It treats SU3, the strong force, as a lower coherent state compared to U1, electromagnetism.
Lower coherence. Now, hang on. That seems counterintuitive. The strong force is incredibly powerful, right? It binds nuclei together against immense repulsion. How is that lower coherence?
That's a great point. It seems paradoxical at first glance. It comes down to the nature of the coherence involved. Think of it like this. Electromagnetism, governed by U1, has long-range symmetry. It has free charge carriers like electrons and photons that can travel across vast distances. It operates almost like a perfectly tuned large orchestra, where every instrument plays in harmony across a huge space, with very little internal friction or self-interaction among the force carriers, the photons. That represents a higher coherence state, broad, smooth, long-range order.
And the strong force, SU3.
The strong force is characterized by things like quark confinement. You never see a free quark. They're always tightly bound inside protons, neutrons, other hadrons. And gluons, the force carriers, they interact strongly with each other. This leads to a much more localized, intense, almost turbulent interaction inside the nucleus.
So, powerful but messy and confined.
Powerful but localized, yes. This internal complexity, the self-interaction, the confinement, this represents a significant loss or reduction of that primordial universal coherence. It's a strong but localized coherence, not a universal frictionless one like U1. U1 is higher coherence precisely because of its long-range order and the lack of self-interaction among photons.
I see. So the framework views the transition from that low coherence SU3 state to the higher coherence U1 state as a coherence gradient. It's not just a mathematical trick breaking down symmetries.
Exactly. It's presented as a fundamental physical process, not just a mathematical operation like group theoretic decomposition. This implies the fine structure constant, alpha, related to U1, and the strong coupling constant, related to SU3, are not independent entities.
They're intrinsically related.
Intrinsically related via a fundamental coherence eigenvalue, linked directly by this gradient. It's seen as a seamless progression of coherence levels.
That's fascinating. We talk about running couplings in conventional physics, right? Where force strengths change with the energy scale you're probing.
Yes, a well-established phenomenon.
Coherence physics doesn't just describe this variability, it claims to explain its origin.
That's a key distinction, yes. What's truly groundbreaking here is the claim that gauge couplings, the strengths of these interactions, are determined by the fraction of total coherence retained after a symmetry reduction event.
So alpha, the fine structure constant, isn't just a number we measure.
No, it's presented as the residual coherence ratio between electromagnetism and the strong interaction. Its apparent stability, why it seems so constant across most experiments we do, is because it's a fundamental coherence eigenvalue. It's a natural inherent property emerging from this coherence landscape.
And this reframes the whole idea of force unification. It's not just about finding one big symmetry group that contained the others at the Big Bang.
Exactly. It's not simply embedding different symmetry groups into a larger one. Unification, in this view, is the restoration of coherence. It happens when the coherence differentials, the gradients between interactions, vanish. It's about reaching that state of maximal unified coherence again.
Okay, so we're not necessarily looking for a single giant mathematical group that contained SU3, SU2, and U1. We're looking for a state where all these different coherence levels just flatten out, equalize.
Like finding that fundamental, perfectly smooth pond from which all the ripples originated? Yes. Or perhaps to which they might return under the right conditions.
And this brings us right back to that famous number, 11,037, alpha. This is where coherence physics gets really exciting and predictive, isn't it?
It really is. Alpha has been this source of immense fascination and, frankly, deep frustration for physicists for, almost a century now.
Since the early days of quantum mechanics.
Right. We mentioned Feynman worrying about it. That highlights this deep desire to understand where it comes from. Previous attempts often relied purely on group theory. For example, looking at symmetry-breaking pathways like S breaking down into U1 times SU3.
Did those work?
Well, they produced approximate ratios, numbers like 1.125 or 1.333. Tantalizingly close to things related to alpha, but never exactly alpha itself. And Lillian points this out as a critical signal.
A signal that something was missing.
Exactly. It meant there was a missing element in those purely mathematical group theoretic approaches, namely what he calls coherence loss dynamics.
Meaning, just looking at the symmetries on paper wasn't enough. You needed to understand how coherence was actually being lost or changed in the transitions. It's a dynamic process, not just a static blueprint.
Precisely. You need the physics of the transition, not just the before and after symmetry labels. Coherence physics addresses this directly. It models the transition from the low coherence SU3 state, that strong force domain, to the higher coherence U1 state, electromagnetism, as a continuous exponential decay of coherence.
An exponential decay, like radioactive decay, but for coherence.
Similar mathematical form, yes. And this decay is parameterized by a single constant, C, a universal measure, supposedly, of this specific coherence loss rate. And here's the truly remarkable part.
Go on.
By solving a strikingly simple equation, 2 times e to the power of minus c equals 11,137, where 1137 is alpha, the model derives the value of c.
It derives c. It's not just putting c in to make it fit.
No, c emerges from the requirement that this exponential decay precisely bridges the gap to yield alpha. The derived value is c, approximately equal to 5.613.
That's wild. This specific number, 5.613, it's not just fitted, it's derived from the relationship between coherence decay and alpha itself. This is huge. I mean, for decades, physicists have tried to find a fundamental origin for alpha, often using approximations or fitting parameters that never quite felt right.
Right.
The fact that C emerges directly from this relationship, it implies it's not just mathematical convenience, it's a deep inherent property of the universe's coherence architecture. Like finding the hidden factory setting for a universe everyone thought came with arbitrary dials.
That's an excellent way to put it. C is not presented as an adjustable parameter. It emerges directly. It establishes itself within this framework as a universal coherence eigenvalue.
Okay, wow.
But the revelations don't actually stop there. Further analysis within coherence physics suggests something maybe even more profound.
More profound than deriving alpha.
Well, connected to it. It suggests that the inverse square root of the fine structure constant, that's 1 divided by the square root of 137, which is approximately 0.0854, is actually more fundamental than alpha itself.
More fundamental. How can a calculation from alpha be more fundamental?
Because this value, P0854, is proposed to directly correspond to the intrinsic coherence factor of SU3.
The strong force's own coherence level.
Yes. Its fundamental unity, or orderedness, is precisely fixed at this ratio relative to electromagnetism. It's claimed to be a direct, intrinsic property of the strong interaction structure within the UFT, and the constant C was 5.613, which we just derived.
Yeah.
physically represents the natural decay rate of coherence during that transition, from the strong interactions domain to the electromagnetic interactions domain. It's the fundamental rate of this coherence loss as the universe unfolds these interactions.
Okay, so if C is truly universal, representing this fundamental decay rate, it should logically pop up elsewhere in physics, shouldn't it? Connecting things that seem unrelated.
Exactly. That's a key testable aspect.
Mm.
The theory predicts that if C is indeed universal, it should appear in other physical phenomena, establishing deep connections. You'd expect to see its influence in, say, QCD energy scales, the typical energies where the strong force dominates.
Makes sense.
Also influencing the peaks of nuclear binding energies where nuclei are most stable. And even subtle differences in the masses of particles like pions.
Wow.
And perhaps most surprisingly, the theory suggests it might even play a role in the thermodynamics of black holes, linking the quantum world directly to the most extreme gravitational phenomena via this coherence constant.
So the really profound takeaway here is the fine structure constant is not some isolated arbitrary number that just happens to be a love 137.
Yeah.
It's a residual effect of a deeper coherence relationship. It acts as a bridge, a direct numerical link between quantum chromodynamics, electromagnetism, and the structure of the nucleus itself. It's a signature of how coherence plays out in the very fabric of the universe. That's a truly mind-bending connection. Okay, let's delve deeper into how this new framework actually plays out inside the atomic nucleus. Because coherence physics apparently has some really insightful and, importantly, testable implications for nuclear physics. Specifically, how does this coherence scaling factor, that 1 over the square root of 137, affect the fundamental building blocks, protons and neutrons?
Right, this is where it gets very concrete. What's fascinating is the direct application of that derived coherence scaling factor, 137, which is about 0.0854, applying it directly to the masses of the proton and the neutron.
Okay, they're measured masses.
Yes. Conventionally, we know the proton mass is around 938.27 mega-electron volts. The neutron is slightly heavier, about 939.57 MeV. They differ by roughly 1.3 MeV.
A small difference, but crucial for things like beta decay and which isotopes are stable.
Absolutely. It's a very significant difference. However, when you apply this 0.0854 coherent scaling factor to these masses, the results are, well, quite striking. They offer a new perspective.
Tell us more. What happens when you scale them down by this factor?
The proton mass, 938.27 MeV, when scaled by 0.0854, becomes approximately 80.16 MeV. The neutron mass, 939.57 MeV, scales to about 80.27 MeV.
Whoa, wait. The difference between them.
Exactly. The conventional difference of 1.3 MeV compresses dramatically in this coherent scaled framework. It shrinks to just 0.11 MeV.
A mere 0.111 MeV difference. That's an astonishing reduction. What does this compression tell us about protons and neutrons in this view?
The key insight proposed here is that this suggests nucleons, protons, and neutrons are fundamentally almost identical coherent structures. Their underlying reality is much more similar than their raw masses suggest. That 1.3 MeV difference we measure arises largely from how they manifest, but their core coherence difference is only this minimal intrinsic offset of 0.11 MeV.
Almost identical coherence structure.
Yes. And here's where it gets really predictive and testable. This tiny 0.11 MeV value. It actually matches certain low-energy nuclear transition energies that are observed experimentally.
Really? It shows up in actual nuclear spectra.
That's the claim. This implies that this small energy difference isn't just some random noise or an arbitrary parameter. It functions as a fundamental quantum, a basic energy packet in processes of nuclear reconstitution and transformation. It's potentially a direct, measurable signature of this underlying coherence principle right there in nuclear physics data.
That's a very specific and exciting prediction, linking a derived constant directly to observed nuclear phenomena. What about pions? They're the lightest mesons, right? They mediate the residual strong force between nucleons. Do they show similar scaling effects?
They absolutely do. And it reinforces the model significantly, suggesting this isn't just a fluke with nucleons. It shows the potentially pervasive nature of these coherence relationships within the nuclear realm. Applying the same 0.0854 coherence factor to the pion masses, we find similar compressed differences that are remarkably insightful.
Okay, what are the numbers?
The charged pion, pi plus or pi minus, has a mass of about 139.57 MeV. When you scale that by 0.0854, it comes down to approximately 11.92 MeV. The neutral pion, pi 0, is a bit lighter, around 134.98 MeV. That scales to about 11.53 MeV.
And the difference between them when scaled?
The coherent scale difference between the charged and neutral pions is just 0.39 MeV.
0.39 MeV. Is that number significant too? Does it show up anywhere?
Highly significant, according to the theory. Similar to the nucleon difference, this 0.39 MeV difference also appears to match certain energies observed in nuclear hyperfine and isomeric transitions. These are extremely sensitive probes of the nucleus's internal structure and energy levels.
Wow.
This suggests that the pion mass splitting isn't just some isolated consequence of the strong force, a purely QCD artifact. Instead, it's intimately tied to the coherence balance with electromagnetism. It acts as another bridge between the two forces. The fact that both nucleons and pions exhibit these characteristic coherence-compressed mass differences, well, it underpins the idea that nuclear structure fundamentally obeys these universal coherent scaling laws. It provides compelling numerical evidence for the framework.
So these mass differences, which have always been a bit tricky to explain precisely from first principles in QCD, are potentially unified and explained under this single coherence principle. That's quite something. But how does this idea apply to something as fundamental and well-known as the nuclear binding energy curve, the one that peaks around iron 56 and nickel 62?
Ah, yes, the binding energy curve. This is truly a beautiful and elegant reinterpretation of a cornerstone of nuclear physics. That familiar curve, which plots the average energy required to remove a nucleon from a nucleus versus the mass number, it's reinterpreted within this framework as fundamentally representing a coherence gradient, or you could call it a coherent stability profile.
So it's not just about how tightly things are bound energetically, it's about how coherently they're configured.
Precisely. It's about the quality of the internal order and structure measured by coherence.
Okay, let's unpack this for the different regions of the curve. What does that mean for the light nuclei at the beginning, like deuterium, helium?
For light nuclei, way down at the low end of the binding energy curve, the framework shows they have low coherence scaled energies. This indicates incomplete nuclear coherence. They are, in a sense, coherence deficient. Their internal arrangement isn't optimal yet.
So fusion?
Fusion, then, isn't just about smashing nuclei together to release energy due to mass defect. It's reconceptualized as a fundamental coherence enhancement process. By merging, these lighter nuclei increase their overall coherence concentration. They move energetically closer to a more balanced, more coherent state, higher up the binding energy curve towards the peak.
And the energy release we see in fusion
Is seen as a direct byproduct of the universe, achieving this higher coherence balance. It's the system settling into a more ordered, more coherent, and thus more stable configuration. It's a fundamental drive towards greater coherence.
And what about the mid-mass nuclei? Those around the peak of carbon, oxygen, and especially iron 56 and nickel 62, famously the most stable elements.
Iron 56 and nickel 62, right at the peak of the curve, they represent the absolute peak of coherence balance within the nuclear domain. They are the most stable configurations possible because they have achieved the optimal internal coherence. All the internal relationships, the arrangements of protons and neutrons, are maximally aligned and efficient from a coherence perspective.
So you can't get more energy out by fusing or splitting them.
Exactly. No nuclear reaction can extract additional net coherence from these elements without putting energy in. They are at the bottom of the coherence energy valley, so to speak, a state of maximal internal equilibrium, making them the most energetically favorable nuclear structures.
And then as the curve declines for the really heavy nuclei, lead, uranium, those guys, what does their state of coherence tell us?
For these heavy nuclei, beyond the peak, their declining coherence scaled energies indicate excess nuclear complexity. There's too much going on, too many nucleons crammed together. There's an imbalance in their coherence. They actually exceed the optimal coherence threshold that the mid-mass nuclei embody.
And this excess drives fission or alpha decay.
Precisely. This excess coherence, or perhaps incoherence due to complexity, drives processes like fission or alpha decay. These are fundamental mechanisms for these heavy nuclei to shed complexity and redistribute that excess coherence into smaller, more stable fragments or particles. The implication here is profound. Which nuclear stability isn't just governed by that delicate tug-of-war between Coulomb repulsion, protons pushing apart, and the attractive nuclear strong force holding them together. It's fundamentally governed by these pervasive coherence gradients. It's all about achieving and maintaining an optimal coherent state, and the universe's inherent drive to return to that state if perturbed.
So what does this all mean for how nuclear reactions like fusion and fission actually happen? It's not just about mass turning into energy via EMC-COP, but fundamentally, it's all about balancing coherence.
Yes, if we connect this to the bigger picture, It really does reevaluate the energy transformations in these processes. It views them as part of a grand act of coherence redistribution across the universe. In coherence physics, fusion and fission aren't really opposites in the way we might think.
Not opposites. How so?
They're described as complementary expressions of the same underlying principle. That principle is the universe's inherent drive towards optimal coherence redistribution. They serve the same cosmic imperative, just from different starting points.
That's a fascinating way to put it. We usually think of them as entirely distinct pathways for releasing nuclear energy.
Well, they are distinct mechanically, of course, but they both serve the same underlying goal: to reach an equilibrium coherent state where the nuclear structure is maximally stable and ordered. For fusion, remember, it occurs when light nuclei are coherence deficient.
Too simple, not optimally configured.
Right. Merging them increases their overall coherence concentration, moving them closer to that iron-nickel peak stability zone on the binding energy curve, which is also the peak coherence zone. The enormous energy release we observe is viewed as a direct byproduct of achieving this higher, more stable coherence balance. It's like the universe exhaling as it finds a more ordered state.
And fission, then, is the mirror image, but still part of the same balancing act, shedding coherence instead of gaining it.
Exactly. Fission happens when heavy nuclei exceed optimal coherence concentration. They're too complex, too crowded. Their internal coherence is strained by things like Coulomb repulsion. Splitting them reduces this internal complexity. It effectively redistributes that excess coherence into smaller, more stable nuclei, the fission fragments. The released energy represents this excess coherence being shed from the system as the nucleus adjusts itself towards a more stable coherence configuration.
It's the universe's way of reducing that structural tension, that incoherence.
Precisely. So these processes aren't just about converting mass into energy according to Einstein's famous equation, although that certainly happens. More fundamentally, in this view, they're about reaching a specific coherence equilibrium, a fundamental state of balance and order.
Okay, that makes sense for fusion and fission. What about the spontaneous decay pathways we see in radioactive elements, alpha, beta, gamma decay? How do those fit into this coherence framework?
They fit in beautifully. Decay processes are understood as intrinsic coherence self-adjustment mechanisms. They are the nucleus's built-in ways of correcting internal coherence imbalances when they arise.
So each decay type is fixing a different kind of coherence problem.
Essentially, yes. Take alpha decay. A heavy nucleus emits a helium-4 nucleus, the alpha particle. Now, the alpha particle itself is a remarkably stable, highly coherent unit. 2 protons, 2 neutrons. So by emitting this prepackaged unit of coherence, the heavy nucleus quickly reduces its own excess coherence concentration or complexity. It's like shedding a perfectly balanced, coherent building block to regain overall stability for what remains.
Okay. And beta decay, where a neutron flips to a proton or vice versa, changing the element.
Beta decay is seen as adjusting the proton-neutron balance within the nucleus. Its goal is to improve the coherence symmetry inside. This process is often linked, the theory suggests, to those small-scale coherence mismatches, like that subtle 0.11 MeV-nucleon coherence difference we discussed earlier. It's a fine-tuning mechanism for the proton-neutron ratio to optimize internal coherence.
And gamma decay, the emission of high-energy photons.
Gamma decay is like the final polish. It releases residual electromagnetic incoherence after a nucleus has already reconfigured itself through alpha or beta decay, or maybe after a nuclear reaction. It acts as a final coherence cleanup, shedding the last bits of disorganization or excess energy in the form of high-energy photons to reach a truly stable ground state.
So each type of decay is a specific, self-regulating mechanism for the nucleus to fine-tune its internal coherence. And this implies there are quantifiable coherence thresholds that actually trigger these decays. It's not random when a nucleus decides to decay.
Yes, that's a key predictive aspect of the model. Each decay mode is proposed to be triggered when the nucleus crosses a specific coherence threshold. This threshold is envisioned as a quantifiable boundary, perhaps defined by the ratio of its coherence concentration, CT, to its incoherence factor I concepts we need to define more clearly.
We'll get to CT and I, but this threshold idea neatly explains why very heavy elements like uranium, thorium, the transuranics are inherently unstable, right?
Absolutely. For these really massive nuclei, their excessive number of nucleons dramatically increases the incoherence, primarily through the ever-growing Coulomb repulsion between all those protons, but also potentially through inherent geometric asymmetries in how all those nucleons are packed. together. They are naturally pushed beyond the stability threshold.
And that's why they spontaneously decay, often through these long, complex chains of transformations, until they finally reach a stable isotope like lead.
Precisely. This coherence redistribution occurs via these spontaneous decay chains. The nucleus sheds mass and energy, often through multiple alpha and beta decays, step by step reducing its incoherence until it reaches a coherence-permitted configuration, a stable state. Endpoint isotopes, like the very stable lead-208, are described within this framework as being coherence-locked. They've reached their optimal coherence balance for their size and can't easily decay further.
That's a neat picture. Does it have implications for astrophysics too, like how elements are made?
It does. The astrophysical implication is also quite profound. In stellar nucleosynthesis, particularly during the extreme conditions of supernova, where heavy elements are forged, these elements are formed in states that temporarily exceed the normal coherence threshold. They're created in highly unstable configurations. The subsequent post-explosion decay chains that we observe across the cosmos are interpreted as the universe's fundamental way of correcting these cosmic coherence imbalances. It's the universe driving these freshly synthesized heavy elements back towards long-term stability and coherent equilibrium over cosmic timescales.
That's a truly elegant way to unify decay, stability, and even cosmic processes, seeing them all as different manifestations of coherence, seeking its equilibrium state. But can we actually quantify this coherence in a measurable way? Can we put numbers to it and use it to predict how stable a nucleus will be?
Yes, and this raises that important question. If coherence is so fundamental, can we measure it and, more importantly, predict with it? Coherence physics introduces specific metrics for this. The first is coherence concentration, abbreviated as CT.
Coherence concentration, CT. What does it measure?
It's defined as a measure of the total coherence stored within a nucleus. It reflects things like its structural symmetry, the efficiency of its nuclear arrangement, and how tightly bound it is its binding efficiency. Crucially, the theory proposes that higher CT values directly correspond to greater nuclear stability.
So the more coherently organized and tightly bound a nucleus is, the more stable it tends to be. That makes intuitive sense. But how is the CT actually measured or approximated in the real world? Can we get a number for it?
Practically, yes. CT can be approximated from observable nuclear properties that we already measure. Things like the nuclear binding energy per nucleon, that familiar curve again, and also from the nucleus's half-life data. Stable isotopes, for instance, the ones that essentially last forever, would naturally have high CT values. They retain their inherent coherence over exceptionally long timescales, often billions of years.
And unstable isotopes?
Unstable isotopes, conversely, would exhibit lower CT values. Their internal structure simply cannot hold that ideal coherence indefinitely, and so they must redistribute it via decay over shorter periods.
Okay, so CT represents the stored coherence linked to stability. What about the opposite of coherence, the measure of its instability or asymmetry? You mentioned an incoherence factor.
Exactly. That's the second key metric, the incoherence factor, usually denoted as I. This factor quantifies the degree of asymmetry or instability within a nucleus. Conceptually, it represents the internal disorder or tension that actively drives a nucleus toward transformation or decay.
How is I estimated?
It can be approximated quite simply as the inverse of the half-life. So I is approximately 1 divided by T to the half-life.
Ah, so a short half-life means a large I. High incoherence.
Precisely. A high I value indicates rapid coherence loss, characteristic of short-lived, highly unstable isotopes. Conversely, a low I value points to slow coherence loss, which is typical for very stable or extremely long-lived isotopes, like uranium-238. You can think of I as representing the pressure for nuclear transformation, how quickly coherence needs to be shed or reconfigured to restore stability.
Okay, let's unpack this. So we can potentially quantify a nucleus's fundamental balance, its internal coherence versus its drive to transform using just these two factors, CT and I.
Yeah.
And use that to predict its behavior. That seems like a significant step beyond just cataloging half-lives.
It is. What's really fascinating here is that it aims to offer a comprehensive, potentially first principles way to classify nuclear stability, moving beyond just simple half-life measurements or traditional binding energy arguments alone. This leads directly to the defining metric of this framework for stability, the coherence signature, or SC.
SC, coherence signature. How is that defined?
It's elegantly defined simply as the ratio of the two factors we just discussed. SC equals CT divided by I. SC equals CTI.
Okay, CT over I. What does this ratio tell us?
This single number provides a powerful predictive index for stability. A high SC indicates high stability. Why? Because it means you have a large coherence concentration, high CT, coupled with a slow rate of decay, low I. The nucleus is very coherent and loses that coherence very slowly. Conversely, a low SC indicates low stability, meaning a smaller inherent coherence concentration, low CT, and or a rapid rate of decay, high I.
Can you give us some concrete examples? How does this SC metric apply to different elements we know? Let's take something heavy but relatively stable, like uranium-238.
Okay, uranium-238. It's a massive nucleus, so it has a high coherence concentration, CT, due to its large mass and strong overall binding, storing a substantial amount of coherence. Crucially, though, it has an extremely low incoherence factor because its half-life is incredibly long, about 4.5 billion years.
So high CT, very low I.
Right. That combination results in a very high SC value. This signifies remarkable stability for such a massive element. It's a testament to its relatively high internal coherence compared to its very slow decay rate.
Okay. What about something notoriously unstable, like, say, polonium-210? It decays much faster.
Polonium-210 is a great contrast. It possesses a moderate coherence concentration, CT. It's a heavy nucleus, but not as large as U-238. However, it has an extremely high incoherence factor.
Yeah.
Its half-life is incredibly short, only about 138 days.
So moderate CT, but sky-high I.
Exactly. This leads to a very low SC value. This low SC indicates rapid and immediate coherence redistribution is needed, which happens via alpha decay in its case. It's essentially a nucleus under immense coherence pressure, desperately trying to shed its excess instability and reach a more balanced state.
And what about carbon-14, the one we use for archaeological dating? How does its SC compare? Where does it fit?
Carbon-14 is an excellent mid-range example. It has a moderate CT, that's a relatively light nucleus, and also a moderate I. Its half-life is around 5,730 years long by human standards, but short compared to U-238, so its SC value falls in the mid-range.
Reflecting its slow, predictable decay.
Precisely. It reflects its slow, predictable transition through beta decay, which is exactly why it's so useful for dating ancient organic materials over timescales of thousands of years. The key insight here is that the SC metric aims to provide a universal, coherence-based stability index, applicable across the entire periodic table, allowing for potentially precise predictions of decay pathways and long-term stability trends based directly on these fundamental coherence principles, rather than just empirical observation or simpler models. It's proposed as a true classification system rooted in coherence.
This is truly mind-bending. It suggests that the nucleus, which, we often picture as this tiny, separate entity deep inside the atom, just sitting there, is actually quietly pulling strings on the electron cloud, affecting the chemical world we experience every day.
That's one of the most provocative implications, yes.
A key prediction of this coherence framework, as I understand it, is that the nucleus's coherent state, its internal order and stability, can directly influence the structure of the electron orbital surrounding it. How does that even work? This goes way beyond standard quantum mechanics, doesn't it? Which mostly relies on the Coulomb interaction, the electrical attraction, and basic quantum numbers.
It does go beyond the standard picture, absolutely. This is one of the most intriguing and, frankly, revolutionary extensions of coherence physics because it genuinely attempts to bridge the gap between nuclear physics and atomic chemical physics in a new way. While traditional quantum mechanics focuses primarily on that electrostatic attraction between the positive nucleus and the negative electrons and the quantum rules governing electron orbitals, SPD, F shells, etc.,
Right.
This new framework posits something more. It suggests that the nucleus's internal symmetry, its stability level, quantified perhaps by that SC value, its overall coherent state, this invisible but fundamental property, can create subtle yet potentially measurable modulation effects on the energy spacing and the overall stability and configuration of the electron shells.
Modulation effects, like the nucleus is causing ripples in the electron cloud.
That's a good way to think about it. It implies a deeper, more intertwined relationship than simply a static point charge attracting electrons. The nucleus isn't just a passive anchor. It's an active participant whose internal state influences its surroundings.
So the nucleus isn't just a static ball of positive charge at the center. It's more like a dynamic coherence engine that somehow interacts with that delicate electron cloud structure. And you mentioned there are simulations that actually support this prediction?
Yes, the theoretical work includes numerical simulations exploring this coupling. These simulations reportedly show that electron shells can exhibit observable coherence oscillations when they are mathematically coupled to these subtle nuclear coherence effects.
Coherence oscillations in the electron shells, what does that mean physically?
Initially, these oscillations show was described as enhanced amplitude. Physically, This could mean there's increased structuring in the electron energy levels. It's like the nuclear coherence is actively helping to shape the electron cloud, making its energy levels and configurations more pronounced or specific than they would be otherwise.
But then it settles down.
Yes. Over time, according to the simulations, these oscillations undergo exponential damping. This indicates a stabilizing influence from the nuclear coherence. The whole atom-nucleus system settles into a new, more stable equilibrium configuration that reflects this coupling.
So if I'm getting this right, it's almost like the universe is playing cosmic Jenga with atoms. When the nucleus gets disturbed, maybe after a decay, or if it's excited, it creates these ripples, these coherence oscillations in the electron cloud. But then the nucleus's coherence helps to quickly re-stabilize the electron structure, like the Jenga tower settling after a block is pulled.
That's actually a surprisingly good analogy for the dynamic interaction described.
So nuclear coherence interacts most strongly with the electronic field right after a change happens in the nucleus, and then it settles into a stable pattern influenced by that nuclear state.
That's the interpretation. It suggests the nucleus state isn't just providing a static positive charge background for the electrons. It's a subtle, perhaps vibrating and actively influencing presence that reaches out to shape the electron cloud. And this has potentially profound implications for the entire field of chemistry.
How so?
Because if nuclear coherence truly influences electron shells, even subtly, then the chemical properties of elements are not purely electronic in origin. That statement alone, if true, is a seismic shift in our understanding.
That is a massive statement. I mean, we always teach and think of chemistry as being entirely dictated by the outermost electrons, their configurations, and how they interact. What specific measurable effects are predicted if nuclear coherence actually plays a role?
The framework predicts several fascinating, potentially testable effects that could really push the boundaries of experimental chemistry and physics. For instance, it predicts that ionization energies, the energy you need to pull an electron completely off an atom, might subtly shift depending on the coherent state of the nucleus.
So different isotopes of the same element, which have the same number of electrons but different nuclei, might have slightly different ionization energies beyond just the simple mass effect.
Exactly. This implies isotopic effects that go beyond just the minor mass differences we usually account for. Typically, isotopes have identical electron configurations, so their chemical properties are considered almost identical, with only tiny mass-dependent variations like slightly different reaction rates, kinetic isotope effects.
But this suggests there could be something more fundamental at play, an intrinsic nuclear factor directly influencing the electron's energy levels.
Precisely. It also predicts that bond strengths could vary slightly for isotopes of the same element. This variation would be due to differences in their underlying nuclear coherence signatures, their SE values perhaps, even if they have the exact same number of electrons and the same basic electronic structure.
So a C12 atom might form a slightly different strength bond than a C14 atom in the same molecule beyond just mass effects.
That's the kind of subtle effect predicted. Furthermore, the theory suggests that catalytic behavior in certain elements might be subtly enhanced or reduced by specific nuclear coherence patterns within their nuclei. This could potentially lead to entirely new avenues for designing more efficient catalysts by selecting specific isotopes known to have favorable coherence properties.
So let's take two isotopes of, say, hydrogen, deuterium, 1 proton, 1 neutron, and tritium, 1 proton, 2 neutrons. Traditionally, we expect almost identical chemical behavior, apart from mass effects making tritium react slower. But this theory suggests they might actually exhibit slightly different reactivity profiles or subtle changes in their spectroscopic signatures in really high-precision experiments because their nuclei have different coherent states.
That's exactly the kind of testable prediction. It offers clear, verifiable avenues for experimental validation, pushing the boundaries of precision chemistry, spectroscopy, and materials science. If these effects exist, they'd be small, but potentially detectable with modern techniques.
And this also ties into phenomena we already observe, like hyperfine splitting and isomeric transitions, offering new explanations.
Yes, the nuclear coherence framework claims to offer natural and perhaps more complete explanations for these phenomena.
So for hyperfine splitting, we usually explain that very tiny energy splitting by the magnetic interaction between the nucleus's spin and the electron orbitals, right? A small magnetic effect.
Right. In coherence physics, however, hyperfine splitting is viewed potentially as a deeper manifestation. It's seen as the nuclear coherence field itself directly interacting with the electronic field. It's not just a simple magnetic dipole interaction. It's potentially a direct intrinsic interaction stemming from the underlying nuclear coherence patterns influencing the coherence patterns of the electron cloud.
A coherence interaction.
In a sense, yes. And for isomeric transitions, where an excited nucleus stays in a higher energy state for a measurable time before decaying via gamma emission, the framework suggests that these excited nuclear states might subtly influence the electron shells through what could be called coherence transfer. This could potentially alter atomic spectra or the probabilities of certain electronic transitions in ways not fully captured by current models that treat the nucleus and electrons as more separate.
So the consequences are quite significant. Hyperfine structures might need to be recalculated using these new coherence-based coupling terms, possibly refining our understanding beyond purely magnetic interactions. And isomer lifetimes might even hypothetically vary slightly depending on the ambient coherence environment, suggesting a direct dynamic link between nuclear stability and the surrounding field conditions.
That's the kind of deeper implication suggested. If we connect this to the bigger picture, it really does open up entirely new avenues. Imagine precision material science, where we could understand and maybe even engineer quantum chemistry at a much deeper level by considering the nuclear coherence state. Designing materials with unprecedented control by understanding this nuclear electronic coupling. This is quite a vision.
This theory is really pulling at the threads of, well, almost everything we thought we knew about fundamental physics, connecting microphysical phenomena like nuclear transitions and electron shells right back to fundamental constants like alpha. Let's talk about the grandest implication of all, force unification. How does coherence physics redefine what it even means to unify the fundamental forces of the universe?
Right, this is really where the ambition of the theory shines. What's truly fascinating here is that coherence physics fundamentally redefines the entire concept of unification. In the conventional view, unification usually means embedding the known gauge groups, SU3 for strong, SU2 for weak, U1 for electromagnetic,
into a bigger overarching symmetry group, like SU5 or SO10 or something even larger.
Exactly. A larger group that hypothetically existed at extremely high energies, maybe right after the Big Bang, and then somehow broke apart as the universe cooled, giving rise to the distinct forces we see today.
Okay. How is coherence physics different?
In coherence physics, unification isn't seen as the reversal of this symmetry breaking, trying to get back to that single larger mathematical group. Instead, unification is understood as the restoration of coherence across all interactions.
Restoration of coherence. So it's not about finding a bigger box to put all the forces in, but about finding a state where all the different coherence levels or coherence gradients just become equal, where there's no more distinction between them in terms of coherence.
Precisely. Remember the universal field tensor, the UFT? It represents the maximally coherent state, that primordial unity, that perfectly structured cosmic tapestry we talked about earlier. Gauge groups, and therefore the forces we observe, emerge when this perfect coherence gets reduced through specific structured gradients or pathways of coherence loss.
Okay.
So, the strengths of these forces, the coupling constants, they aren't arbitrary numbers that just pop into existence. They become coherence-derived quantities, direct readouts of these coherence dynamics. The key insight, then, is that force unification occurs when the coherence differentials vanish between the interactions.
When the coherence levels equalize.
Yes, not just when they happen to share a hypothetical parent gauge group mathematically.
Yeah.
It's a much more dynamic and process-oriented view of unification. It's about the physical state of coherence itself.
That's a powerful and, again, elegant shift in perspective. Now, you also mentioned this idea of hyperdimensional embedding effects. That sounds like it's taking things even further, suggesting our familiar forces are somehow tied to higher dimensions. How can forces inherit dimensional properties? That sounds very sci-fi.
It does sound a bit abstract, but let's try to visualize it. Imagine a grand, intricate, multidimensional sculpture. Maybe that's a better picture of a universal field tensor in its full, maximally coherent form. What we observe as SU3 or U1, the strong electromagnetic forces in our everyday world, aren't separate, independent carvings just sitting on a flat surface.
Okay.
They're more like shadows or projections of different parts of that larger, higher dimensional sculpture onto our familiar 3+1 spacetime, our three spatial dimensions plus time. So when the coherence of the UFT reduces or projects down to form these specific forces we experience, they retain a kind of memory or residual property from that higher order symmetry, that higher dimensional structure from which they originated.
A memory of the higher dimensions.
In a mathematical sense, yes. This memory then subtly influences their effective strengths and how they relate to each other in our observable reality.
And this is what potentially explains why constants like 1137 alpha and 137, that 0.0854 factor, appear so consistently across nuclear physics, atomic physics, maybe even cosmology, because they are, in essence, universal projection ratios from this deeper, higher dimensional reality into ours.
Yes, that's the core proposition. For example, that 0.0854 SU3 coherence factor, the inverse square root of alpha, could be interpreted as a universal projection ratio, a geometric factor describing how that aspect of the hyperdimensional structure projects into our observed 3+1 spacetime. It suggests a deep, perhaps geometric origin for these fundamental constants. Their values aren't arbitrary. They're inherent properties of how higher dimensions manifest in our lower dimensional reality.
Wow. Okay. So does this framework extend to gravity and the electroweak interactions too, to complete the picture of unifying all the known fundamental forces?
It aims to, absolutely. The framework provides a fascinating interpretation for gravity. It's viewed not primarily as a particle-mediated force in the traditional sense, like exchanging gravitons, though that might be reconcilable. Instead, gravity is seen more fundamentally as a long-range coherence structuring principle.
A structuring principle.
Yes, it could emerge from the lowest frequency coherence modes of the UFT, essentially the slowest, broadest waves or patterns of coherence permeating spacetime. This perspective offers a natural explanation for why gravity is vastly weaker than the other forces.
How so?
Because it operates at a completely different, much lower coherence scale. It's like comparing a deep, slow, rumbling bass note, gravity, to the sharp, high-frequency notes of electromagnetism, or the strong force. They're all part of the same music, but at vastly different frequencies or coherence levels.
That's an interesting analogy. And what about the electroweak interaction, the theory that unifies the weak force and electromagnetism at high energies?
The SU2 AQ1 mixing, which underpins the electroweak theory, is seen within coherence physics as a coherence blending process. The fact that the W and Z bosons, which mediate the weak force, are massive, while the photon, electromagnetism, is massless. This is interpreted as resulting from partial coherence reductions during the symmetry breaking.
So their masses come from coherence loss, not purely from interaction with the Higgs field as in the standard model. Or maybe the Higgs mechanism itself is a manifestation of this coherence reduction.
That's the direction it points. It suggests the Higgs mechanism might be understood as part of this broader coherence reduction process. This alternative perspective, focusing on coherence blending and reduction, might even lead to alternative, perhaps more fundamental calculations for things like the electroweak mixing angle, that crucial parameter determining the relative strengths of the weak and electromagnetic components.
So in this grand unified picture emerging from coherence physics, SU3, SU2, U1, and even gravity are all just different coherent states or manifestations of the same underlying universal field tensor. Their dramatic differences in interaction strength arise naturally from coherence gradient magnitudes and these proposed hyperdimensional embedding properties rather than from completely independent physical origins that we then struggle to unify.
That's the ultimate vision, yes. A truly holistic and intrinsically interconnected view of the cosmos, rooted in the dynamics of coherence.
This sounds like an incredibly comprehensive and, well, elegant theoretical framework. It really seems to tie together so many disparate observations under one conceptual umbrella. But, for any new theory to gain traction, especially one this ambitious, it needs to offer concrete, testable predictions. Does coherence physics actually provide a clear roadmap for experimental validation? Can we go out and check this stuff?
Yes, and that's absolutely crucial, isn't it? A theory without testable predictions remains speculation. Coherence physics, as described, excels here by providing what seems to be a clear, detailed roadmap for experimental verification across different energy scales. It predicts specific, quantized energy differences in nuclear transitions, for example, that are directly tied to those fundamental constants we keep mentioning. 1137 and perhaps more directly 13137 or 0.0854.
Quantized energy differences, meaning specific, discrete energy values should pop up.
Exactly. It means we have precise numbers to look for in experiments.
So those subtle energy values we derived earlier from the coherence scaling, like the 0.11 MeV nucleon coherence difference and the 0.39 MeV pion coherence difference, the theory predicts these should actually show up as distinct energy signatures in laboratory measurements in nuclear spectra.
Precisely. That's the prediction. The framework suggests that the 0.11 MeV nucleon coherence difference should appear repeatedly and consistently in low-energy nuclear transition spectra across many different isotopes where nucleons are rearranged. Finding that specific energy recurring would be a potential smoking gun, a clear signature of these coherence effects at play.
And the pion difference, 0.39 MeV.
Similarly, the 0.39 MeV pion coherence difference should correlate directly with specific hyperfine transitions or isomeric nuclear transitions, particularly in nuclear systems where pions are known to play a significant role in the binding energy dynamics. Again, this offers a very specific energy target for high-precision nuclear spectroscopy experiments to look for.
Okay, and what about the nuclear binding energy curve itself, that fundamental stability profile we discussed? How can that be tested more rigorously through this coherence lens?
The prediction there is that the nuclear binding energy curves, when appropriately scaled by 1137, or related factors, according to the theory's methodology, should produce the same universal coherent stability profile across all stable isotopes. It should reveal an underlying universal shape related to coherence, consistently peaking near iron and nickel when viewed through this scaling lens.
How would you verify that?
The verification approach would involve using high-precision gamma spectroscopy to identify nuclear transitions that precisely match these predicted coherence quanta, 0.11 MeV, 0.39 MeV, etc. We can also meticulously compare spectral shifts in isotopes that have similar nucleon numbers but different predicted coherent signatures, different SE values, to detect the subtle differences in energy levels or transition probabilities that the theory predicts should exist due to nuclear coherence influencing the electrons. This level of precision is becoming increasingly achievable with modern detector technology.
That's fascinating. Predicting specific quantized energy values that experimentalists can actively search for in nuclear data. What about going to much higher energies? High-energy scattering experiments, like the ones smashing particles together at the Large Hadron Collider, LHC. Does the theory make predictions there too?
Yes, it extends to high-energy regimes as well. In high-energy collision experiments, the theory predicts specific signatures that would potentially deviate from the expectations of the standard model alone. For instance, that SU3 coherence factor, the 0.0854 number, 1137, it should potentially appear in the ratios of cross-sections between processes dominated by the strong force, as SU3, and those dominated by the electromagnetic force, U1, particularly at specific energy scales where the transition between these regimes might be probed. We'd be looking for this specific numerical ratio emerging directly from the particle interaction data.
So we literally see this ratio, more than 0.0854, pop up in how often certain types of particle interactions happen at incredibly high energies, potentially validating its role as a universal projection ratio or coherence factor.
That's the kind of prediction, yes. Additionally, the coherence gradients themselves, the transition regions, might produce unexpected features like plateaus or perhaps even new resonance peaks in hadronic scattering data. Scattering involving protons, neutrons, pions, etc. Features that would be distinct from conventional QCD predictions alone.
Okay. And those hyperdimensional embedding effects you mentioned, could they show up at the LHC?
They might. The theory suggests they could reveal themselves as specific energy thresholds, where coupling ratios, the relative strengths of forces, shift in discrete steps, rather than changing smoothly and continuously as predicted by standard running coupling calculations. It would be like finding a sudden, precise change in that projection ratio as we crank up the collision energy past a certain point.
So the path forward for experimentalists could involve reanalyzing existing deep inelastic scattering data, where we probe inside protons and neutrons, to look for these coherence-derived scaling patterns. Or maybe comparing hadronic versus leptonic, electron-muon, scattering results very precisely at intermediate energy regimes to look for signatures of these predicted SU3 to U1 coherence transition gradients.
Exactly. That offers a clear, actionable path forward for experimentalists. Their findings could either provide strong confirmation for this coherence framework or potentially refute its specific predictions, which is how science progresses.
And the implications, you said, stretch even further, beyond particle accelerators and nuclear labs, right into the grandest scales of cosmology and the super enigmatic realm of black hole physics.
Absolutely. The theory doesn't shy away from the big cosmic questions.
So what does this all mean for those huge questions about the universe, its origin, the fundamental nature of black holes, and maybe even dark matter, that invisible stuff that seems to make up most of the matter in the universe, but we can't directly see?
Well, if we connect this coherence framework to the bigger picture, it truly offers a profound new interpretive lens for some of these greatest cosmic mysteries. Take the very early universe, for instance. The conventional Big Bang model often relies on invoking extreme, almost unimaginable temperatures and densities right at the beginning to explain how the fundamental forces separated and how structure eventually emerged.
The symmetry-breaking epochs.
Right. Coherence physics offers a potentially different narrative. Force separation could be reframed as coherence reduction cascades, occurring as the universe expanded and cooled, rather than solely high-temperature symmetry breaking. This might potentially remove the need for such extreme, singular initial conditions to explain the eventual formation of galaxies and large-scale structure. It could offer a smoother, more dynamically driven picture of cosmic evolution.
That would be a significant simplification, or at least a different perspective on the universe's very beginning. And what about black holes, those ultimate cosmic enigmas?
The fine structure constant, alpha, understood now as a fundamental coherence eigenvalue, might play a direct role in black hole thermodynamics. Things like their entropy and how they handle information.
Yeah.
Lillian suggests that event horizons, the boundary of no return around a black hole, could act as critical coherence boundaries.
Coherence boundaries.
Yes, boundaries where the extreme gravity enforces a certain coherence condition. This could influence how the structure and information of things falling in are redistributed, perhaps encoded into the subtle quantum patterns of the outgoing Hawking radiation spectra. It provides a new, coherence-based way to think about the infamous black hole information paradox, whether information is truly lost or just scrambled and preserved in a highly coherent way.
Fascinating. And dark matter, that huge component of the universe that seems invisible and non-interactive except through gravity. Any coherence explanation for that?
Coherence physics proposes a really intriguing possibility here. It suggests that certain coherence-locked states might exist. These would be configurations of the underlying UFT that are extremely stable, very high SC value perhaps, but crucially do not interact significantly via the electromagnetic force, or maybe even the strong force.
So they'd be stable, massive, but invisible.
Exactly. Their existence and stability could potentially be predicted from looking for extreme solutions within the coherent signature model. It suggests dark matter isn't necessarily some exotic new particle that we just haven't found yet in our accelerators. Instead, it might be a manifestation of extreme, highly stable coherent states of the fundamental field itself, states that simply don't couple to light, making them effectively invisible to our current detection methods except through their gravitational influence. It offers a truly novel, non-particle-based hypothesis for one of cosmology's biggest and most persistent puzzles.
Wow. Okay, let's try and sum this up. We've explored 22nd century coherence physics, this breathtaking framework proposed by Philip Randolph Lillian. It attempts to fundamentally unify phenomena we previously considered quite disparate. The fundamental forces, the intricate structure and stability of the atomic nucleus, and even the subtle behavior of atomic electron shells. It seems to redefine concepts we thought we understood, like fusion, fission, radioactive decay, viewing them not as independent processes, but as universal expressions of coherence redistribution within this singular underlying universal field tensor. This is really a profound reimagining of reality's very foundations.
It really is ambitious in its scope, and we've seen some of its truly remarkable claimed achievements. Perhaps most notably, the potential first principles derivation of the fine structure constant both alpha 1137 and its inverse square root, approximately 0.0854, identifying them as fundamental coherence eigenvalues. No longer just arbitrary numbers measured in labs, but derived properties of coherence itself.
And we've unpacked its seemingly unified interpretation of nuclear energetics, explaining why those nucleon and pion mass differences, when looked at through this coherent scaling lens, compress down to specific quantized values like 0.11 MeV and 0.39 MeV. And crucially, these values appear to directly match known low-energy nuclear transition energies found in experiments. It's also provided this new, elegant way to understand the nuclear binding energy curve as a coherence stability profile, where maximum stability equals optimal coherence.
We also introduced that innovative coherence signature, SC metric. Calculated as coherence concentration CT divided by the incoherence factor, it offers a potentially powerful predictive index. A way to quantify nuclear stability based on these underlying coherence properties, allowing for a universal classification and prediction of nuclear behavior across the entire periodic table.
And maybe one of the most surprising and importantly testable links, the suggestion that nuclear coherence has a subtle but direct influence on the structure and energy levels of the electron shells surrounding the nucleus. This implies that chemical reactivity is not purely electronic in origin, and it provides potentially elegant new explanations for phenomena we already observe, like hyperfine splitting and isomeric transitions. It could fundamentally change how we approach quantum chemistry, maybe opening up entirely new avenues for research and materials design.
And critically, underpinning all of this, the framework offers a profound path towards force unification. It reframes unification not as a simple merging of mathematical symmetry groups, but as the equalization of coherence levels across all interactions. The concept of hyperdimensional embedding aims to explain why certain constants in fundamental coupling relationships appear universally, and it extends its reach naturally to include gravity and the electroweak interactions, offering a truly unified vision of all of nature's forces emerging from coherence dynamics.
And finally, as we just discussed, it provides a clear, actionable roadmap. Concrete, testable, experimental predictions for both microphysical systems like nuclear spectroscopy and high-energy scattering experiments, and for tackling those grander astrophysical questions about the early universe, the true nature of black holes, and even the perplexing enigma of dark matter.
It's important to stress this isn't just presented as a minor tweak to existing physics. It's proposed as a genuine paradigm shift, a fundamental restructuring of our understanding. It aims to provide a first principles origin for constants and phenomena previously taken as purely empirical, bridging long-standing gaps between fields that often seem disconnected, like nuclear physics, particle physics, quantum field theory, and cosmology. It presents a vision of reality that is fundamentally more dynamic, structured, and interconnected, where coherence is revealed as the primary underlying language of nature.
So, if coherence physics, or something like it, is eventually validated through these rigorous experimental tests, just imagine the possibilities. From perhaps truly understanding the very beginning of the universe without relying on seemingly contrived extreme initial conditions, to potentially engineering entirely new forms of energy release through coherence-based extraction methods, or even designing materials with unprecedented precision by learning how to subtly manipulate this proposed nuclear electronic coherence coupling. How might you listening rethink the hidden order of the universe and the fundamental forces that govern everything within it after this deep dive? Thanks for joining us for this profound exploration into 22nd century coherence physics. We'll be back soon with another fascinating deep dive.